proposed a reflection model that is widely used in computer graphics. The Phong reflection model is a simple model that can be computed rapidly. It has three terms: a diffuse term, a specular term, and an ambient term. It uses four vectors to calculate the color of an arbitrary point P on a surface. The first vector is the direction in which the light source is located. The second vector V is the direction where the viewer or the camera is located. The third vector N is the surface normal, calculated based on the orientation of the surface. And the final vector, vector V, is the vector that defines the perfect reflector of I with respect to the normal vector N. So if light comes from this direction, it is perfectly reflected in this direction because the angle with normal here and the angle with reflection here should be equal. So let's look at some surface type. For smooth surfaces, the reflected light concentrates more in the direction that is a perfect mirror-like reflection of the incident light. So if this was the normal angle, these two angles would be equal. For rough surfaces or diffuse surfaces, the reflected light scatters in all directions. So no matter where the viewer is located, it will get some of this scattered or diffuse reflected light. Surfaces are perfectly diffuse reflectors. They scatter light equally in all directions. The amount of light reflected is proportional to the vertical component of the incoming light, or cos of theta I. Cos of theta I can be calculated as a dot product between L vector and the N vector. So L dot N will give us cos theta I, where L and N are both normalized to unit vectors. There are also three coefficients, the red, green, and blue, that show how much of each color is reflected by the object. These are defined by the surface properties. Whereas a diffuse surface is rough, a specular surface is smooth. Smooth surfaces show specular highlights due to incoming light being reflected in all directions, concentrated close to the direction of a perfect reflection. Look at this sphere. We see a specular highlight at a point, and this highlight is not just one point, it slowly dies away. And the color that it shows is not the color of the sphere, because the sphere here is blue colored, whereas the center of the highlight is white, which is the color of the light source. Phong proposed using a term cos phi raised to the power alpha that drops off as the angle between the viewer and the ideal reflection increases. So it is defined with this equation. The reflected light is proportional to a component Ks, which is where the S stands for specular. So it's the specular reflectivity coefficient of the surface. So it's a surface property. I is the incoming light. And this is the shininess coefficient. Alpha is known as the shininess coefficient of the material. And this is how we calculate how much of this light would be reflected from point P. This is a symbol of proportionality. The values of the shininess coefficient alpha can be set between 100 to 200 for metals, and small values from 5 to 10 to give like plastic-like appearances. And this plot shows how the umbrella of reflection changes. The concentration of reflection changes with different values of alpha. If alpha is large, all reflections are concentrated to a very small angle, and if alpha values are small, the reflections are scattered between minus 90 and plus 90 degrees, which are the opposite of specular reflection. As explained before, ambient light is the result of multiple interactions between large light sources and objects in the environment. Amount and color depend on both the color of the lights and the material properties of the object. So we can add an ambient component Ka, Ia to the diffuse and specular terms to get our final reflection from a point. So Ka is the reflection coefficient of the surface, the ambient reflection coefficient of the surface. Ia is the ambient intensity of the light, and we do not have either an angle term or a distress term here to attenuate this light, because this light is present everywhere in the scene.